Good evening, everybody. Professor Barlow, Physics 215, Northampton Community College, Physics for Scientists and Engineers. We're going to be starting chapter 19 tonight. We're going to be talking about heat and the first law of thermodynamics. As usual, bring any questions to our Zoom sessions. You can ignore anything that is an asterisk at the beginning of the chapter, anything that has an asterisk next to the section, you can ignore those sections. We're going to be skipping those. So here's going to be a list of what we're going to be talking about. We're going to talk about heat as energy transfer, internal energy, specific heat, calorimetry and solving problems in calorimetry. Calorimetry and latent heat are a big part of this chapter. We're going to go over the first law of thermo. We're going to talk about molar heat for gases. We're going to talk about the concept of adiabatic expansion of gases, and we're going to talk about heat transfer. Heat transfer is only done through conduction, convection, or radiation. Okay. So we often talk about heat as though it was like some type of material or substance or fluid, like, water, as though it flows from one object to another. That's not really the right way to think about it. The right way to think about it, heat is a form of energy. It's not a material that flows. So for heat, we're going to use calorie as the unit for heat. 1 calorie is the amount of heat necessary to raise the temperature of 1 gram of water by 1 degree Celsius. So hopefully that's a review for most of you. Don't be fooled by calories on a food label. Food labels refer to kilocalories, the heat necessary to raise a kilogram of water by 1 degree Celsius. But what we're doing is calorie, the amount of heat needed to raise 1 gram of water by 1 degree C. So heat is a form of energy. It's possible to equate it to other forms of energy, like mechanical energy, right? The experiment shown below is Joule's experiment for how to measure heat energy, okay? The experiment below found that the mechanical equivalent of heat by using a falling weight, 4.186 joules is the equivalent of 1 calorie, or 4.186 kilojoules is equal to 1 kilocalorie. So what you can see here is they took this weight, or Joule took this weight, hung it from a pulley, and that pulley is kind of, if you're looking at the front face of it vertically, and then he turned the other pulley 90 degrees so it would spin a series of paddles inside of a tank, inside of a fluid, water. And as the weight fell, it would increase the temperature of the water in that tank. Okay. So the definition of heat. So let's start off with defining what heat is. Heat is energy transferred from one object to another because of a difference in temperature. Remember that the temperature of a gas is a measure of the kinetic energy of the molecules in that gas. So if you wanted to work off extra calories, how much work would you need to do to compensate for a dessert that had 500 calories? Okay, so if you ate this dessert that's 500 calories and you decided to climb stairs or go on a backpacking trip and climb a mountain, how much height would you need to climb to work that off in terms of calories? So I'm going to switch to a whiteboard. Okay. So we are going to assume that an average person weighs about 60 kilograms. And we are going to use what we talked about before and say that since this was a food label, that it's actually 500 kilocalories. And we were given this conversion, 4.186 times 10 to the third, or 4,183 joules in 1 kilocalorie. So that's my conversion. You'd need to work off 2.1 times 10 to the 6th joules. We know from previous chapters that this would be work, right? Work is equal to this potential energy, right? If we were to solve this for the height, how many stairs we would need to climb or whatever, you'd have to figure out the work that you would put in divided by mass times gravity. I'm going to bring this down. 2.1 times 10 to the 6th joules of energy. 60 kilogram person. Your individual mass may vary. 9.8 meters per second squared is gravity. So you would need to climb 3,600 meters. That is a lot of steps. Okay. That was pretty easy, right? So the sum total of all the energies of all the molecules in a substance is its internal or thermal energy. Temperature measures the molecule's average kinetic energy. So internal energy, or the total energy of all the molecules. Heat is the transfer of energy due to some differences in temperature. So those are some useful definitions for the rest of the chapter. Internal energy of an ideal atomic gas is given by E, internal energy, N, which would be your number of molecules, 1/2 mv squared, and this is, note that this is an average velocity. Since we know average kinetic energy in terms of temperature, you can rewrite this using that Boltzmann's constant. So if a gas is molecular, if the gas is molecular rather than atomic, okay, and you look at rotational, vibrational, kinetic energy, all of that needs to be accounted for, okay? So we're going to talk now about specific heat. Specific heat is the amount of heat required to change the temperature of some material, okay? And it is proportional to the mass and temperature change. So as the mass and temperature change go up, that amount of energy is going to go up. So you talk about Q in hydraulics, but you also talk about Q in physics and in heat. Q is the amount of heat. So this uppercase Q refers to the amount of heat. M is the mass of whatever the substance is. C is your specific heat. Now take notice here that we have a nice table that you can look up the specific heats of all these different substances. There's two columns, one in kilocalorie per kilogram per degree C, and one that's in joules per kilogram per degree C. Be careful which C you're using, okay? Most of the time, we're going to be using this column over here, okay? We're going to be using joules per kilogram degree C, not kilocalorie, okay? So if we were to rearrange this equation and solve for C, you would end up with Q divided by M delta T, and that's where you get these units. Q is a form of energy, so that's J, heat energy, divided by the mass, kilograms, and delta T is change in temperature, degrees C. So that's how you get these units by rearranging this to solve for C. The specific heat is a characteristic of the material, okay? On a test, you would either be given this table or you would be given the C as a known, or it would be the one thing that you would be solving for in the note of the text of the problem. So let's do an example. How heat transfers depends on specific heat. So how much heat input is needed to raise the temperature of an empty 20 kilogram vat that's made of iron? So let's go back and look at this. Iron has a specific heat of 450. Okay. And what if the vat was filled with water? Okay. Well, water has a specific heat of 4186 if it's a liquid. If it's ice, it has a specific heat of 2100. If it's steam, it has a specific heat of 2010. Okay. So how much heat input is needed to raise the temperature of the iron vat from 10 degrees C to 90 degrees C? So I'm going to switch over to a whiteboard. So I'm going to clear this off. So for part A, just the iron vat, how much heat is needed is Q, MC delta T. They gave us the mass of the iron vat. That's the 20 kilograms. Now be careful the units that you're working in, right? Specific heat is joules per kilogram degrees C. So if I gave you something that was in grams, unit conversions, you'd have to know how to convert that over to kilograms. Joules per kilogram degrees C. So in these types of problems, you can let the units guide you to where to plug things in and how to set it up. So our delta T, we're going from 10 degrees to 90. So T final minus T initial is 90 minus 10, right? Which is 7.2 times 10 to the 5th joules, or 720 kilojoules, 720,000 joules. So this is the Q that's required just to raise the temperature of the iron. So how much heat do we need to raise the temperature of the water? Okay. Same equation, right? Q MC delta T. Okay. They gave us that we're going to fill this with 20 kilograms of water. So the 20 kilograms of water, notice that it is a much higher specific heat, 4186 joules per kilogram degrees C. 90 degrees minus 10 degrees, right? If you're going to raise the temperature of the water from 10 to 90, you'd need 6,700 kilojoules. You need a lot more heat. You don't need as much heat for the cast iron or for the iron vat. Because, well, why is that? Why is the heat needed to raise the temperature of this iron vat that weighs the same? Notice that they weigh the same. Well, heat is a conductor. Okay, it wants to pass that energy off to whatever is in it. Okay, so the metal pan wants to transfer that heat energy to the water. You need a lot more energy to raise the temperature of that water, though. So I'm going to go back to the PowerPoint. Okay. So how do we do these types of calorimetry problems? We'll talk about a calorimeter here in a second, but we'll talk about, so actually let's talk about the calorimeter now, right? A calorimeter is, it's what you use to transfer heat energy, okay? So you have some type of closed system where no mass is going to enter or exit the system. Energy can be exchanged from one item to another, okay? In an open system, mass can transfer as well. So that's the difference between open and closed. Open, mass can transfer. An isolated system is a closed system where no energy in any form is transferred. So for an isolated system, energy out of one part equals energy into another part, or another way to say that is heat lost is equal to heat gained. Okay, so I'm going to skip forward here real quick and talk a little bit more about what a calorimeter is. Okay, you have a thermometer going into sort of a closed insulating jacket or an outer container. Then you have a calorimeter cup that goes inside of that. And there's usually some sort of insulation. It can just be an airspace. And you have something that is stirring whatever the liquid is. In this case, it's water. So the instrument to the left is, this picture is a calorimeter, okay, which makes actual quantitative measurements of heat exchanged, okay? Some sample is heated to a well-measured high temperature. Then we put it into water and the equilibrium temperature is measured. From that, you can get the specific heat of whatever the sample is and then compare it, and then you can figure out what that material was. So I jumped ahead. I'm going to go back and we're going to do this example. We're going to talk about tea. Okay. We're pouring the tea into a small ceramic cup. If you have 200 cubic centimeters of tea at 95 degrees C, and it is poured into a 150 gram glass or ceramic cup that starts off at 25 degrees C. Now, a couple things to note here. First of all, the cup is measured in grams, not kilograms. Tea is going to be close enough to water unless I gave you a different specific heat. So we're going to use the temperature, the specific heat, excuse me, of water. And we're also going to use the density of water. Okay, because we're given a volume, okay, of the tea. So we're going to substitute in the volume, or I'm sorry, the density of water. So what will the common final temperature of the tea in the cup be when equilibrium is reached? So we're just assuming the instant that they reach equilibrium, right? If you leave them in the room for long enough, the temperature is going to continue to go down because both the tea and the cup are going to lose their heat to the outside surroundings over a long enough time span. So we're not waiting until that occurs. We're just measuring to the instant that the tea and the cup meet their equilibrium temperature. So I'm going to stop sharing this, and I am going to start sharing a whiteboard. Clear that. Okay. So we have to deal with some of the assumptions first. We're going to assume that the tea is going to behave a lot like water. And the specific heat of water is the 4186 joules per kilogram degree C. So that would either be given to you or we would give you the table. The mass of something is its density times its volume. Well, we know the density of water is 1 times 10 to the third kilograms per meter cubed. Now, I know that my C is in kilograms. So I want to do this conversion for the mass to get to kilograms. If we were given 200 cubic centimeters, 200 centimeters cubed, I'm going to do the unit conversion right away. You can kind of do this on your own. 200 centimeters cubed is the equivalent of 200 times 10 to the minus 6th meters cubed. Okay. On a test or in the homework or in the lab, show me that unit conversion to get from here to here, but that's a relatively simple unit conversion. So your mass would be 0.20 kilograms is what the mass of the tea going into the cup is. Okay. We know that Q is equal to MC delta T, but we have the tea in the cup. We want to know the final temperature, Q of the tea, Q of the cup. So T is the subscript T is for the tea in the cup, and the C is for the cup itself. So for the tea, it's 0.20 kilograms, 4186 joules per kilogram degree C. Our final temperature, or I'm sorry, our initial temperature of the tea is 95. So you're starting off with 95. Okay. So this is the initial temperature of the tea. We don't know the final temperature of the tea. Okay. We're given that the cup is 150 grams. 150 grams is 0.15 kilograms. Glass or ceramic. Ceramic and glass kind of behave similar enough that we can use 840 joules per kilogram degree C. Now, the glass cup is initially at 25. Okay, so it is going to come up from 25. So notice how I did 95 minus T. This is sort of the trick with this problem. The temperature of the tea is going down. The temperature of the cup is going up, right? So the cup is initially at room temperature at 25 degrees C, right? So this is, notice how in this side I have to go 95 minus T, but on this side I have to go T minus 25 because the cup is going to go up in temperature while the T is going down in temperature. Okay. So really, what I'm left with here is an algebra problem. I end up with 9,500, which is joules, minus 837 T is equal to 1,260 T minus 3,150. I get a final temperature of both the tea and the cup of 86 degrees. So one of the tricks in this chapter is recognizing that one thing is going down in temperature and one thing's going up in temperature. So the setup here is critical. Okay. So you'll want to do a couple examples of that from the textbook, from the sample problems, from different resources. There's also additional video resources online if you're having trouble with the concept, or you can get with me in a separate Zoom meeting and I can work with you on it. Okay. So we went over this already, and all of these problems are calorimetry based. Okay. We're gaining or losing heat. Okay. So we have an unknown specific heat determined by calorimetry. So an engineer wants to determine the specific heat of some new alloy. Okay. You have a 0.15 kilogram sample of the new alloy heated to 540 degrees C. So we've heated this thing to 540 degrees. It is then placed in a 0.4 kilogram volume or mass of water that's at 10 degrees C, which is contained in a 0.2 kilogram aluminum calorimeter cup. So we do not need to know the mass of the insulating jacket. We're going to assume it's an airspace. And the cup insulates it, so the temperature won't change significantly. So we're going to ignore that. The final temperature of the system is 30.5 degrees C. They want us to calculate the specific heat of this alloy. Okay. They want us to calculate the C of the alloy. So I'm going to stop sharing the PowerPoint and I am going to go back to my whiteboard. I'm going to clear this. So this new alloy, right? The heat lost by this alloy, by this sample, is going to be equal to the combination of the heat gained by the water that's in the calorimeter cup plus the heat gained by the calorimeter itself, the aluminum calorimeter. Okay. So for all of these individual things, you have an MC delta T for all three of these Qs. Okay. So the alloy sample is 0.15 kilograms. We don't know the C. This is what we want to find. We want to find that C. We know that it started off at 540. Okay. And we know that the system reaches an equilibrium at 30.5. Okay. So this side of the equation lost heat. This side of the equation is gaining it. So it's going to be equal to the 0.4 kilograms of the water. The water is the 4186 kilogram, or I'm sorry, joules per kilogram degree C. It starts off at a temperature of 10 and ends at 30. So on this side, we're doing the final, the 30.5 minus the 10. Okay. Plus, the calorimeter is aluminum, 0.2. The cup is 0.2 kilograms. Aluminum specific heat is 900 joules kilogram degree C. And it is going through the same temperature differential that the water in it is, 30.5, 10 to 30.5. So it's going up. The metal is going down. So really the only unknown here is the C. So you do this algebra, you do this algebra, add them together, subtraction times the multiplication, and you're basically rearranging this to solve for C. It's a simple algebraic solution. So the new alloy is 497 joules kilogram degree C, right? 497. So iron and steel are right around 450. So it's probably some derivative of either iron or steel because it's so close to them. Okay. So again, the trick here is recognizing one temperature is going down, the other temperature is going up, and that's how you're doing this difference in the delta T setup. Let's talk about latent heat, okay? Latent heat is the energy required for a material to change phase, okay? Not to raise or lower its temperature, that's specific heat. Latent heat is the energy required for the phase change to happen, even though its temperature is not changing, okay? It needs energy to go from a solid to a liquid to a gas. It needs energy to do that, okay? So this picture here, the graph, is heat added and temperature. Okay, and you can see that this is for water / ice. So you have something that starts out at 0, it's ice. It's kind of a combination of water and ice between 20 and 100. It's all liquid between 100 and 200. It's some water and some steam from 200 to 740, and above 740, it's all water vapor or steam. Okay, so this is the heat input, and these are the temperatures. I'm sorry, my bad, rewind, okay? I was talking about the heat added in kilocalories. The temperatures are from -40 up to 0, it's ice. Okay, it stays water ice at 0 degrees. So notice you can add between 20 and 100 kilocalories of heat. So between 20 and 100 kilocalories of heat is needed to get this to go from all ice to complete water. Notice how the temperature isn't changing. It's just going through that phase change. It will remain liquid from 0 up to 100. And then from 100 up, it's water and steam. It's boiling, right? It's converting to steam, but it won't convert all of it until you get beyond 100 degrees or beyond 740 kilocalories of energy. So the first part of what I was saying, I apologize. I was talking about kilocalories of energy added. So the x-axis is kilocalories of energy added. The y-axis is your temperature in degrees C. So notice that from 200 to 100 kilocalories of energy, you're staying at 0 degrees, right? It's ice at 0, but it's also 0 degrees when it's some ice, some water, right? Latent heat of fusion is the heat required to change 1 kilogram of a material from a solid to a liquid. Latent heat of vaporization is the heat required to change a kilogram of material from a liquid to a vapor. So latent heat of fusion is going from a solid to a liquid. Latent heat of vaporization, liquid to a gas or a vapor. Different materials, different latent heats. You have your melting point, your boiling point, and then your latent heat of fusion, latent heat of vaporization. And notice that we're in kilocalories per kilograms or kilojoules per kilograms. So the heat required for a phase change, latent heat, is Q is equal to ML. Okay. So will all of the ice melt? You have a half a kilogram chunk of ice at negative 10 degrees C is placed in 3 kilograms of ice, of iced tea or tea at 20 degrees C. At what temperature and in what phase will the final mixture be? The tea can be considered as water. Ignore any heat flow to the surroundings, including the container. Okay. So you'd need to look at what the total energy is required to convert all of it, all of the substance, to a liquid, okay, and compare that. So I'm going to stop sharing this for a second, and I'm going to go to a whiteboard. So you know that conservation of energy holds, okay? So all ice, okay, so you have the ice itself and you have the water. So if you have 3 kilograms of water, right, which is the iced tea, but we're going to consider it as water, right, to get to 0 degrees C at 20 degrees. So if we look at this and you say Q MC delta T, this is just for the temperature change part. You have 3 kilograms of iced tea. We're treating it like water, 4186 joules per kilogram degrees C. Degrees C. And your temperature change, 20 degrees to 0. It would be 250 kilojoules. Okay. So this is to change the water from 20 to 0. So if you're going to look at ice going from negative 10 to 0, we were given that it's a half a kilogram of ice. The specific heat of ice, if you go back and look at that table, is different than water. It's 2100 joules per kilogram degrees C, right? Its temperature difference is 10 degrees, right? 0 minus negative 10. So that is 10 and a half kilojoules. The phase change to go from ice to water, this is my latent heat. This is your Q ml. Okay. The latent heat is 0.5 kilograms. The L, which is a lookup value, the latent heat of from going from ice to water, from a solid to a liquid, that is equal to 167 kilojoules. Okay, so 10.5 kilojoules, right, is the temperature change of the ice, plus, to convert all of it to liquid, would be 177 kilojoules. So there isn't enough energy, there isn't enough heat to get it to all liquid between 0 and 20 degrees. Okay, so what we have is we have the heat to raise the ice from -10 to 0, plus the heat to change the ice to water, plus the heat to go from 0 degrees to some unknown temperature, which is what we want, is going to be equal to the heat lost by the starting volume of the T. So we already figured out this first part. This first part is your 10.5 kilojoules. So this first part is right here. My second part is my 167 kilojoules, which is right here, converting the ice to water. Now we're going to look at these two things, which we don't know, but we do know they have to reach some sort of equilibrium temperature. So 0.5, 4186, right? T minus 0 degrees. Here's my 3 kilograms of the T at 4186. Its temperature was 20 degrees. So its temperature is going to go down. The temperature of the ice is going to go up. Rearranging this and solving for the T, it's going to be at equilibrium, the ice slash liquid combo is going to be at 5 degrees C. Okay. Again, the trick is getting this temperature position set right, as far as you're looking at which thing is losing temperature versus which thing is gaining temperature. Okay. So that's the hardest part of this chapter. So some simple steps to keep in mind. Is the system isolated? Are all significant sources of heat energy transfer known, and can you calculate them? Or were you given enough information? Apply conservation of energy. So if there is no phase change, the heat transferred will depend upon the mass, specific heat, and temperature change. If there are phase changes, you need to figure those into your calculations as either latent heat of vaporization, right? Or so you either need latent heat of fusion or latent heat of vaporization. Latent heat of fusion is going from solid to liquid. Latent heat of vaporization is going from liquid to vapor. Okay, those are separate heat calculations. Q equals ml, right? So if there are phase changes, those terms will depend on the mass and latent heat only. Okay. Determine or estimate what phase the final system will be in. Make sure that each term is in the right place and that the temperature changes are positive. There is only one final temperature, okay? And that's the temperature that the whole system will reach equilibrium, and then solve it. Okay, so determining latent heat. You have a specific heat of liquid mercury is 140 joules per kilogram degree C. You have 1 kilogram of solid mercury at its melting point, negative 39 degrees C, is placed in a half a kilogram aluminum calorimeter cup filled with 1.2 kilograms of water. That's at 20 degrees C. The mercury will melt, and the final temperature will be the combination, and it is known to be 16.5 degrees C. What is the latent heat of fusion of the mercury in joules per kilogram? Okay. So we only have one unknown here to solve for. So you can draw yourself a picture. You can set up sort of like a flow chart with words describing what's going on. Okay, so you have the Q that's required to melt the mercury, which is Hg. Q equals ml. Okay, and then you have the Q that is heating the mercury that's in its liquid state, and that is equal to mc delta T. So looking at the first part of this, we're given that it is a 1 kilogram sample. We know that the liquid mercury has a specific heat of 140 joules per kilogram degree C. And our temperature change, right, our final temperature is 16.5. It starts off at negative 39 degrees. So negative 16.5 minus 39. This temperature change is 55 degrees C worth of temperature change. So our Q is 7,770 joules. That's just what the liquid mercury is going through. Okay. So the Q of the calorimeter plus the Q of the water so this is the first part of the problem. Okay. Now we're looking at the calorimeter plus the water Okay. So you have MC delta T for the calorimeter and your MC delta T. So here's the calorimeter and here's the water. So this is, the calorimeter is a 1/2 kilogram aluminum calorimeter. Aluminum has a specific heat of 900 joules per kilogram degree C. Again, just a table lookup or it would be given to you as a known. So the final temperature 16.5, initial temperature 20. So it'd be your 20 minus your 16.5, which would be 3.5. Plus the water, you have 1.2 kilograms of water. Water's 4186. I'm not going to write out the units of it, but please write out the units on a test. 20 minus 16.5. This is degrees Celsius. So this Q of the calorimeter, 19,200 joules. Okay. They want us to find the latent heat of the mercury. Okay, well, the Q calorimeter plus the Q water is also going to be equal to the heat required to melt the mercury plus the temperature change, the heat of the liquid mercury. So the calorimeter is my 19,200 joules. The Q to melt the mercury is ml. So the mass of the mercury is 1 kilogram. So L is my latent heat, plus the Q change of the liquid is up here. This is my 7,770 joules. So all I'm solving for is this L, the latent heat of the mercury, which is 11,400 joules per kilogram. Okay. So stop sharing that. Going back to the PowerPoint here. The latent heat of vaporization is relevant for evaporation as well as boiling. Okay. The heat of vaporization of water rises slightly as the temperature decreases. So on a molecular level, the heat added during a change of state does not go to increasing kinetic energy of individual molecules, but it goes into breaking down the bonds in between those molecules so the next phase can occur. The change in internal energy of a closed system will be equal to the energy added to the system, Q, minus the work done by the system on its surroundings. So change in internal energy is equal to Q minus work. This is the law of conservation of energy written in a form for heat energy transfer. Or it is the first law of thermodynamics. Okay? That is the equation form of the first law of thermodynamics. The definition is change in internal energy of a closed system will be equal to the energy added to the system minus the work done by the system on its surroundings. Okay, so using the first law, you have 2,500 joules of heat is added to the system and 1,800 joules of work is done on the system. What is the change in internal energy of the system? So these types of calculations are usually pretty straightforward. So change in internal energy is equal to Q minus W. So you have 2,500 joules of heat energy. The only thing you got to be careful of is minus work. Well, 1,800 joules of work is done on the system. So when I say work is done on a system, it's positive 1,800 joules. When I say that the work is done by the system, it's negative 1,800. Okay, so this is minus a negative 1,800. Minus a negative is the same as adding a positive. Change in internal energy here is going to be 4,300 joules. So both the heat added and the work on the system add to the system's internal energy in this case. So it increases to 4,300 joules. So just be cautious of the wording. On a system is adding, done by the system is subtracting. Okay. We can extend the first law to include changes in mechanical energy, kinetic energy, potential energy. So change in kinetic, change in potential, plus change in internal energy is equal to Q minus W. Kinetic energy transformed to thermal energy. If you have a 3 gram bullet traveling at 400 meters per second, enters a tree and exits the other side with a speed of 200 meters per second, where did the bullet's lost kinetic energy go? And what was the energy transferred? Well, where did it go? Let's deal with that first. It went into deforming and blowing out the tree and heat exchange, right? So what was it? Well, we need to change in energy is equal to the negative change in work. The change in work, so this is negative, kinetic initial minus kinetic final. So 1/2 mv1 initial squared minus 1/2 mv final squared. 1/2 times a 3 gram bullet, right? 0.003 kilograms times 400 meters per second, and that is squared minus 1/2 times 0.03 times 200 meters per second, and that's also squared. $180 joules goes to deformation and heat transfer. Calculating the first law of thermodynamics, okay? We're going to look at PV diagrams. Volume is on the x-axis, pressure is on the y-axis. So this is a PV diagram of an ideal gas undergoing some isothermal process. Isothermal, temperature does not change, okay? So you have this movable piston. So in order for an isothermal process to take place, we assume the system is in contact with some sort of heat reservoir. So in general, we assume that the system remains in equilibrium all throughout the process. So this top line is isothermal. Again, a PV diagram. You have another process that is called adiabatic. Adiabatic is one in which there is no heat flow in or out. No heat flow is adiabatic. All right. So isobaric on the left is one where it's constant pressure, and isovolumetric is constant volume. So isobaric on a PV diagram is a horizontal line. Isovolumetric is a vertical line on a PV diagram. So the work done in a moving piston by an infinitesimally small element or displacement is given by this equation. Okay. So for an isothermal process, PV equals nRT, if we integrate this, we end up with, this picture that you see below. This is more conceptual in nature than anything, okay? So different paths take the gas from point A to point D in an isovolumetric process because the volume doesn't change. No work is done, and then the gas goes from D to B at a constant pressure. No integration is needed. So work is equal to pressure times change in volume. So it's just the area under that curve that's shaded. So work in an isothermal and adiabatic process. So the PV diagram for a gas expanding in two ways, isothermally and adiabatically, the initial volume at A was the same in each case, but the final volumes at B and C are going to be different. So which process was more work done by the gas? So more work is done by the isothermal process, right? It's above the adiabatic process for the entire length, so the area under the curve is going to be higher. So if we have an ideal gas, right, compressed at some constant pressure, 2 atmospheres, right? All we're doing, change in work, is P delta V. Okay, it's just the area under basically that bottom line, right? So work is equal to P delta V. Pressure, 2 atmospheres. 1 atmosphere is 1.01 times 10 to the 5th Newton per meter squared. Volume, 1 liter, is 10 to the minus 3rd meters cubed. So work is 2.02 times 10 to the 5th Newton per meter squared. 2 times 10 to the minus 3rd meter cubed minus 10 times 10 to the minus 3rd meters cubed. These are the 2 points on the graph, 2 liters and 10 liters. So the work is negative 1.6 times 10 to the 3rd joules. So the negative sign indicates that the heat flows out, so the work is done by the gas. Okay, so change in internal energy is equal to Q minus W, 1600 joules. The positive sign here indicates that the work is done on the gas. The negative sign here is work done by the gas. Okay. So work done on an engine. In an engine, 0.25 moles of an ideal monatomic gas in the cylinder expands rapidly. Okay. And adiabatically against the piston. In the process, the temperature of the gas drops from 1150 Kelvin to 400 Kelvin. How much work does the gas do? So change in internal kinetic energy is final minus initial. So 3/2 NR delta T, temperature final minus temperature initial. So we have 3/2. The number of moles was given to us at 0.25 of a mole. R is a constant, 3.14 joules per mole Kelvin. And the temperature, 400 minus 1150. So it's negative 2300 joules. Negative change. So the work done, negative change in kinetic energy. So the work is 2300 joules. So in a isothermal process, temperature is constant, delta T is 0, so that makes change in internal energy 0, so Q is going to be equal to W. In an isobaric process, pressure is constant, Q is equal to change in internal energy plus W, which is equal to change in internal energy plus P times delta V. Isovolumetric, volume is constant, so change in volume is 0, which makes work 0. So Q is going to be equal to your change in internal kinetic energy. And adiabatic, Q, there is no change in heat energy. So change in internal energy is going to be equal to negative work. So this is how I got that last solution. So for gases, the specific heat depends upon the process. So in an isothermal process, specific heat is different from isovolumetric. Okay. So here you have your CPs and your CVs. So for a gas in a constant volume process, no work is done. For a gas at constant pressure, you have work is your P times delta V. So comparing the two processes for a monatomic gas, the temperature change is Cp minus Cv is equal to this R value. And notice that R value is pretty close to 2. So that second to the last column, all of those R values are close to 2. Right? So change in internal energy, 3/2 NR delta T. So not worried about those, 19.8, 19.9. Okay. Heat transfers. Okay. Section 1910. Heat transfer, you have conduction, convection, and radiation. Conduction can be visualized as occurring through molecular collisions. So changing Q per time is equal to this Ka T1 minus T2 over some length. So things go from hotter to cooler. Okay. So the K in that previous thing is thermal conductivity. So materials with large K values are considered conductors, and small K values are considered insulators. So I'm going to skip this example. Again, K is thermal conductivity. And R, the uppercase R is it's used in building materials. So if you see insulation, insulation has an R value. The higher the R value, the better it insulates. Okay. Convection occurs when heat flows by the mass movement of molecules from one place to another. It could be natural or it could be forced. You know, heat rises. Both examples are considered natural convection. So you have hot water and sections in the water that are cooler, depending upon, you know, how things are flowing in the water and how big this container is. And then you have, like in your house, convection is occurring. Okay. Radiation is a form of energy transfer received from the sun or during some sort of nuclear reaction. You stand too close to a fire, most heat you feel is radiated as well. Energy radiated has been found to be proportional to the fourth power of the temperature. Okay. Not really worried about emissivity. Easy for me to say. Emissivity. Okay. Not really too worried about that for the purposes of this. And not really worried about this example. It goes back and uses this equation. Will not be on the test. This section, again, not on the test. There's some interesting stuff in here about thermography and scans for tumors and other types of infections, but you want to look at it in the text. It will not be on the test. Same thing with the STARS radius. Internal energy refers to total energy of all molecules in an object. For an ideal monatomic gas, internal energy is 3/2 NKT or 3/2 nRT. Heat's the transfer of energy from one object to another due to temperature difference. Heat can be measured in joules or calories. Specific heat of a substance is the energy required to change the temperature of a fixed amount of water by 1 degree C. In an isolated system, heat gained by one part of the system must be lost by another part of the system. Calorimetry measures heat exchange quantitatively. A big part of this chapter and the types of problems that are going to be on the test are going to be calorimetry type problems. Okay. Phase change requires energy even though the temperature doesn't change. Heat of fusion is the amount of energy required to melt 1 kilogram of a material. Heat of vaporization, amount of energy required to change a kilogram of a material from a liquid to a vapor. Again, these types of calculations are going to be big on the test. This type of stuff in the latter part of the chapter isn't as important. In terms of the test, if you're going to be going into different types of engineering, you're going to be revisiting these when you take a thermodynamics class. This is a physics class, so we're kind of touching on the stuff very briefly, but we're not delving into it in extreme depths. You'll be spending an entire semester on this, depending upon your major. First law of thermo, there it is in an equation form. Thermodynamic processes can be adiabatic, which no heat is transferred. Isothermal, where the process is at a constant temperature. Isobaric, it's at a constant pressure. Isovolumetric is at a constant volume. So work done, change in work is pressure times the change in volume. Molar specific heats given by the equation there. This is important. This will be on the test. Heat transfer is either done by conduction, convection, or radiation. Conduction, heat's transferred through the collisions of molecules in a substance. Convection is bulk quantities of substance flowing from one area to a different area based on different temperatures. Radiation is the transfer of energy by electromagnetic waves. And that is the end of the chapter. Please come to the Zoom sessions with questions. Please also feel free to email either myself or Professor Miller or Professor Doney with questions, comments, concerns. We'll be in touch soon, and there's only one more chapter to go, and we are at the end of the class. So we will talk soon to do chapter 20.